All right. Today we're going to be talking about capacitance and capacitors. And this lecture is going to be incredibly similar to our lecture that we just had on inductors. So much so that I'm going to revisit some relationships that we learned about inductors in our last class meeting to show you kind of a shorthand way of getting all of the relationships for a capacitor. So let me just call this part right here inductor review. Okay. So in our last class meeting, we learned the following relationships. We found that the voltage drop across an inductor as a function of time was equal to the inductance multiplied by the derivative of the inductor current with respect to time, which I believe I called equation 1. We also learned that we could rearrange this expression and find that the current flowing through an inductor was given by 1 divided by the inductance value times the integral from negative infinity to t of the voltage drop across the inductor as a function of time. And we also express this as the integral from t naught to t of the voltage drop across the inductor plus some initial condition on the inductor current. We'll call this equation 2. Our third equation was related to the power absorbed by an inductor, which could simply be expressed as the product of the current and voltage. And substituting in equation 1 for the voltage, this could also then be written as L times I times di by dt. Call this equation 3. And then lastly, the energy absorbed by an inductor is expressed as 1/2 times the inductor value times the square of the inductor current. So capacitors and inductors are electrical duals of each other, and we'll talk about more about that in just a little bit. But effectively, all that means is that our relationships for an inductor or inductance can be used for capacitors simply by swapping out I and V. So everywhere we saw a voltage, replace it with a current. Everywhere we saw a current, replace it with a voltage, and we'll wind up getting our capacitor relationships. So realistically, I'm not expecting you to actually have to memorize 8 equations for this material. You can just learn 4 of them, and as long as you know where the I and the V should be for inductors or capacitors, you'll be able to get the others. All right, so let's look at capacitors really quickly. So much like we did on Friday, we're going to discuss briefly what a capacitor is made of. So I'm going to start with a pair of terminals that might be part of some larger circuit, like so. And I'm just going to draw a section of wire here and another section of wire here. And now I'm going to draw the physical part. And so what I'm attempting to draw here is a conductive plate. Typically, this is made of some type of metal, possibly aluminum, steel, anything like that. Doesn't particularly matter. And then down here, connected to the bottommost terminal, is a second plate. So this is an example of what's commonly called a parallel plate capacitor, and the overwhelming majority of capacitors that you could purchase are formed as parallel plate capacitors. Realistically, any two conducting media that are close to each other will exhibit some form of capacitance. But when we place two of them very close together specifically, that's how we form a capacitor like we have illustrated here. So we have what's called a top plate. We have a bottom plate. And then in between these two plates is an insulating material. Now that insulating material can be air, could be a vacuum, but more often than not, it is what's called a dielectric material. So I'm just gonna fill in that region with this pink layer here. We're gonna call this a dielectric medium or a dielectric material. And this constructs our capacitor. So there are a few critical things about capacitance. So let me write that out really quickly. So capacitance is a measure of how a circuit element responds to a changing electric field or changing voltage. So in a capacitor, well, actually, let me backpedal a little bit. So let's talk about what might happen if we were to place a voltage across a capacitor, right? So I'm going to put a positive polarity on top, a negative polarity on bottom, and here is some voltage V, okay? So what's going to happen when we apply a voltage across a capacitor is that negative electrical charge that is found on the top plate will be attracted to the voltage source. And so that's going to wind up leaving behind a charge of positive Q on the top plate. Very similarly, positive charge on the bottom plate will be attracted towards the negative polarity terminal of the voltage that's supplying the drop across the capacitor. And so that's going to wind up leaving behind a negative charge on the bottom plate. And when we have two charges that are separated by some distance, we wind up establishing an electric field. So I'm just going to draw some electric field lines on top here. I will do them in blue so that we can see them. So we're going to have an electric field oriented from the positive charge to the negative charge. So in an inductor, the presence of a current and therefore magnetic field is what led to the energy storage characteristics of that device. In a capacitor, it's the presence of an electric field that allows it to store energy. Now, the energy storage mechanism for a capacitor is actually much easier to understand than it was for an inductor. So let me explain what I mean by that. Okay. Many of us, particularly those who have taken Physics 202 and have had a little bit of field theory, have an understanding that like charges tend to repel each other, right? So if you were to put a positively charged particle near to another positively charged particle, they would try to push each other away, right? Similarly to how like the north pole of a magnet near the north pole of another magnet, they repel each other. Same thing, except this is electric field interaction instead of magnetic field interaction. So effectively, for every charge that we put on either the top plate or the bottom plate, it becomes a little bit harder to put the next amount of charge on that plate. So we have to put work in to moving charge onto the plate. And then when we decrease that voltage, so let's say that we turn the voltage off, all of the work that was put into accumulating charge on the plates gets sent back out into the system in the form of what's called a displacement current. So we store all the energy by putting charge on the plate, and then we let the energy flow back into the circuit when we turn the voltage off. So that's the energy storage mechanism for a capacitor. And like I said, I feel it's much easier to understand what's going on with a capacitor than it was for an inductor. All right, so we have some basic understanding of how a capacitor is constructed. I've given you a simple definition for capacitance, just a measure of how a circuit responds, or excuse me, a circuit element responds to a changing electric field or a changing voltage. So let me give you the circuit schematic symbol really quickly. So the one that we're going to use in this class extensively is this symbol, where we will define our element's capacitance by some number, which I'm just going to call C for right here, stands for capacitance. The voltage drop across the capacitor would be V of C, and the current flowing through the capacitor would be I of C, like so. This is what I'm going to call a general capacitor or an unpolarized capacitor. Now, in some textbooks, YouTube videos, and all of that kind of good stuff, you might see another symbol that is very regularly used to illustrate capacitance. We're going to have the top line the same, and then the bottom line, instead of representing the parallel plates, it's going to have a curve to it, like so. And once again, the magnitude of the capacitance would be given. Here's the voltage drop across the capacitor, and here's the current flowing through the capacitor. While a lot of even textbooks use these two symbols interchangeably, they are technically distinctly different. So this symbol on the right is what's typically used for a, let me actually write it this way, an electrolytic capacitor, which is also commonly referred to as a polarized capacitor. So in a general capacitor, you can apply either a positive voltage or a negative voltage across the capacitor, and it will be perfectly fine. In an electrolytic capacitor, if you were to apply a negative voltage across that capacitor, it would physically rupture. It's due to a chemical reaction inside that lets off a bunch of gas. And so if you ever crack open a piece of electronic equipment and you see a cylindrical capacitor, let me draw something really quick here. So you might see something like this. You would have a cylinder with two legs coming off of it. There's usually a silver stripe down the side, and then the top is typically scored. So you might see an element that looks like this, and if this top scored thing is puffed out, that means that your capacitor has failed because you accidentally put the wrong polarity voltage across it. Electrolytic capacitors are used because you can usually get larger capacitance values out of a smaller form factor using an electrolytic capacitor, but the drawback is you have to have a system where negative voltages for sure are not going to be present, which is why you see them very often in DC power supplies. Okay. All right, let's talk about the units of capacitance really quickly. So capacitance is measured in farads, where 1 farad, or 1F, is equal to 1 amp second per volt. So earlier, or a few minutes ago, I mentioned that capacitors and inductors were electrical duals of each other. And if you replaced current with voltage and replaced voltage with current, you would have the same relationships. Well, if we look at the units of inductance, I'll do that really quickly right here. So 1 Henry, if you recall from Friday's lecture, was 1 volt second per amp. Even the units work out in the exact same way. So it simply swap voltage and current and you have the other relationship. Let's get into our mathematical relationships here really quickly. Actually, before we do that, does anybody have any questions before we move on to the mathematical relationships? All right. So our first relationship is going to be a derivative-based relationship, just like we had for inductors. So this comes from the fact that charge is related to current is related to the derivative of charge. So what we're going to wind up having is that the current flowing through a capacitor is equal to the capacitance value multiplied by the derivative of the voltage drop across the capacitor. This will be our equation 1. And like I said earlier, it is extremely similar to what we saw in an inductor, simply swapping current and voltage. So in an inductor, we learned that for a DC circuit, inductors looked like a short circuit. What do you guys think a capacitor is going to look like to a DC circuit, just based on the fact that everything seems to be opposite between capacitors and inductors?
Maybe an open circuit.
Exactly right. So in a DC circuit, capacitors behave like an open circuit. And we can understand that by looking at this mathematical relationship. If the voltage isn't changing, the current flowing through the element is fixed at 0. So in an open circuit, we know that no current can flow through it while any voltage can appear across its terminals. So that effectively exactly describes a capacitor when there's no change in the voltage. On Friday, we learned that the current flowing through an inductor cannot change abruptly. What do you think that relationship is going to be for a capacitor?
The voltage can't change abruptly.
Yep, it is literally that simple. Anywhere we said current, replace it with voltage. Anywhere we said voltage, replace it with current. So the voltage drop, let's see, the voltage across a capacitor cannot change abruptly. Okay. Absolutely right. So we can move on to our integral-based relationship now. So our integral-based relationship between current and voltage in a capacitor is as follows. The voltage drop across the capacitor is going to be equal to 1 over the capacitance times the integral from negative infinity to t of the capacitor current with respect to time. And this could be expressed as 1 over c times the integral from t naught to t of ic t prime dt prime plus vc at t naught. This will be equation 2. This is the equation that we use when we know what the current is doing and want to know what the voltage is doing. Our power relationship is simply the product of current and voltage, because that's all it will ever be. Sorry, this should be VC. And if we were to substitute in our first equation here, we could write this as C V by the derivative of the voltage. And lastly, our energy relationship is always the integral of power. And this is going to come out to be 1/2 C times the square of the voltage. Right. So these are the 4 equations and the 2 kind of statements that tell us how capacitors behave in a circuit or a system. Okay, I know that I went through that rather quickly, but it's because it's the exact same thing that we saw for inductors, just with the current and voltage swapped. So let's look at in-class assignment problems 1 and 2, much like we did on Friday. Okay. So problem 1 here says, we have a 0.2 millifarad capacitor. So I'm just going to draw something here. So 0.2 millifarads. And in part A, we're given one particular voltage waveform, and we're asked to determine the maximum amount of energy. And then in the second part, we're given a different voltage waveform. We're given a current waveform, and we're asked to determine the voltage. All right, so let me just draw some things here. So here's our voltage. Here's our current. So in part A, our voltage is 5 plus 3 cosine squared, 200 t volts, and we want to get the maximum energy. Let me change that P to a W. So we know that the energy stored by a capacitor is equal to 1/2 C times the voltage drop across the capacitor squared. So I want to ask you guys a question. How do you think we would go about determining the maximum value of our energy? Anybody have any thoughts?
The only way I can really think of would be having t on an integral as like t approaches infinity.
So I'm not 100% sure I'm following what you're saying, so let me offer a couple of different things, okay? So to me, the most obvious way, and it is not the way that I'm going to choose here for reasons that'll be obvious in a moment, would be to take the derivative of this expression and then set it equal to 0 to find some point in time where either a minimum point occurs or a maximum point occurs, and then plug in that value of t into our equation for w, and that should either give us a maximum or a minimum, right? That's the basic way that we learn to find the minimum and maximum of functions in our calculus classes. So if I tried to do something like that, I would wind up having 1/2, I'm just going to leave this as c, and then I'm going to square this ugly voltage function, right? So that's going to look like 25 volts squared plus, let's see, 3 times 5 times 2 would be 30. Cosine squared 200t, and then I'm going to square 3 cosine squared 200t is going to be, actually, let me just write it out this way. Whatever that thing is. We could sort that out with some trig identities and all of that kind of stuff, but we have the square of cosine squared. It's going to be nasty and it's going to be gross. So while it definitely can be done that way using trig identities and stuff like that, it's not the way that I want to go about it. Okay. So we can see from this relationship right here that our energy is proportional to our voltage squared, right? So since our energy is proportional to our voltage squared, I believe it stands to reason that our maximum energy is going to occur whenever our voltage is either at its maximum value or its minimum value. And I say that because we have a square function. If it weren't squared, we would just say if the voltage were at its maximum value, the energy would probably be at its maximum value. So let's look at some things really quickly, right? So if I were to plot 5 plus 3 cosine squared 200t, it's going to look something like this. So we know that there's going to be some DC offset. Because there's a DC term. And then there's also going to be a sinusoidal signal kind of oscillating on top of that. So something like this. So looking at this rudimentary graph, it seems pretty obvious to me that because it's not symmetrical about the horizontal axis, the maximum energy is going to occur whenever the voltage is at its maximum, not when the voltage is at its minimum, because the minimum isn't more negative than the maximum is positive, if that makes any sense. So let me ask you guys a series of questions. When is a constant DC value of 5 volts at its maximum? Or a better way to put this is, what is the maximum value of 5 volts?
5.
5. Absolutely right. What is the maximum value of a cosine function?
1.
So what would be the maximum value of cosine squared?
1.
So what would be the
Negative
maximum
1.
value of 3 cosine squared?
3.
Right. So what's the maximum value of 5 plus 3 cosine squared?
8.
8. So this part right here corresponds to 8 volts. And from this, we could say that we're going to have 1/2. So let's see, C was 0.2 times 10 to the -3 amp second per volts times 8 volts squared. So the volt squared over volts, that's going to get rid of this guy down here. So we're going to have amps times seconds times volts, which is the same thing as a joule. When we plug all of those numbers in, let me grab a calculator really quickly. We're going to wind up having 0.5 times 0.2 times 10 to the -3 times 8 squared comes out to be 0.0064 or 6.4 times 10 to the -3 joules, which is the exact same thing as 6.4 millijoules. So we could have thrown a bunch of calculus and trig at this problem, and we would have gotten the right answer in about 25 minutes, right? So sometimes it pays to literally just think your way through the relationship as opposed to always just relying strictly on the math, okay? Any question about that particular problem or the process that we involved? All right, so part B is a little bit more straightforward, okay? So in part B, we're asked to determine the voltage present across the capacitor terminals if VC is 0 for all points in time up to t is equal to 0, and it is, and IC of t is 8e to the -100t milliamps for t greater than 0. Okay, so let's write some things down here. So for part B, we know that IC of t is 8e to the -100t milliamps for t greater than 0. And we know that VC of t was 0 volts for t less than or equal to 0, effectively. So our goal, if I'm not mistaken, is to find V of t. So we know what the current's doing. We're trying to figure out what the voltage is, which means we need to be applying our second equation. So our second equation, just to remind you guys, was V of t is equal to 1 over c times the integral from, t naught to t IC of t prime dt prime plus VC at t naught. So now I'm simply going to substitute in the information that we're given. So scroll back up here, 0.2. So 1 over 0.2 times 10 to the -3 amp seconds per volt. That's my 1 over c times the integral. So what's my T naught here? Anybody have any thoughts?
Zero.
0, absolutely. So we're just going to integrate from 0 to t because we're looking for a voltage as a function of time. Now we're going to substitute in our capacitor current relationship. So that's 8 times 10 to the -3 amps e to the -100t prime dt prime. And then we're going to add our initial condition in, which was given as just 0 volts. So a couple of things we can see here from the jump. we have a 10 to the minus 3 in the numerator, a 10 to the minus 3 in the denominator, so those guys cancel each other out. We have an amps in the numerator and an amps in the denominator, so those guys cancel each other out. So it looks to me like we have 8 divided by 0.2, which turns out to be 40 volts per second. Now we need to integrate e to the minus 100t. How do I do that?
You just divide by negative 100.
Divide by negative 100. All right, so I'm going to have 1 over negative 100. And the units here should be per second. We talked about why that is in our last class meeting. Then I'm going to have e to the minus 100 t prime evaluated at t and 0. So just looking at the units here, seconds and per seconds cancel. 40 divided by negative 100 is going to look like negative 0.4. So I'm going to have negative 0.4 volts multiplied by e to the minus 100t minus 1. So that's going to look like 0.4 minus 0.4 e to the minus 100t volts, which is the same thing as we have up here, except I expressed it in millivolts instead of volts. So any questions regarding part B of this problem? Like I said, I think it's a little bit more straightforward. Okie dokie. So looking at problem 2, we have a 5 microfarad capacitor, and we are given a current waveform, and then we're asked to find voltage, power, and energy at particular points. So as a reminder, the voltage drop across a capacitor is 1 over c times the integral from t naught to t of the capacitor current with respect to time plus the voltage at t naught. Here we're told the voltage at t naught is equal to 0, which means that part right there is just going to get thrown away because it's simply 0. So for part A here, we're asked to determine the voltage drop across the capacitor at a particular point in time. How do you guys think we could do that?
It'll just be area under the curve at that time, right?
Exactly right. So luckily for us, and you should expect to see something like this on your exam, the waveform that we are given is formed completely of simple triangles, right triangles and rectangles, right? So if we're looking at what's going on at t is equal to 5 milliseconds, effectively we're looking for this area. I'm going to call it A1. This area right here, I'm going to call it A2. And this area right here, I'm going to call it A3. And I'm just going to add those areas together and then multiply by 1 over c. So V at 5 milliseconds is going to look like 1 over 5 microfarads. So let me write that out. 1 over 5 times 10 to the minus 6 amp seconds per volt. And now let's work on our areas. So how would I describe that area A1, or how would I calculate that area A1? What's the
1/2
formula?
base height.
1/2 base times height. Absolutely right. So 1/2. So the base to me looks like 2 milliseconds. So that's 2 times 10 to the minus 3 seconds. And the height to me looks like 15 milliamps. So that's 15 times 10 to the minus 3 amps. Let's look at what that does with respect to our units just really quickly here, right? So we have a second in the numerator canceling out that second in the denominator. We have an amps in the numerator canceling out that amps in the denominator. So it's looking like things are going to go well for us to get voltage, because that's the only unit that we have left. All of the other areas should have the same units, so all of that kind of good stuff will cancel out. So what should the area A2 be? How do I find that?
Just base times height.
Just base times height, because it's a simple rectangle. So our base is once again 2 times 10 to the minus 3 seconds. And our height is once again 15 times 10 to the minus 3 amps. And then for the area A3, because it's a rectangle, it's just going to be base times height again. So our base is 1 times 10 to the minus 3 seconds. And our height is -5 times 10 to the minus 3 amps. Close all that off. So let's see, 0.5 times 2 times 15 plus 2 times 15 plus 1 times -5 gives me 40. I have 10 to the minus 3 times 10 to the minus 3, so that's 10 to the minus 6. So that's going to cancel out that 10 to the minus 6 there. So I simply divide that 40 by 5, and that's going to give me 8 volts. Anybody have any questions, comments, or concerns about how we calculated part A? All right. For part B, we're asked to determine the power absorbed by the capacitor at a particular time. So I think the easiest way to do this is to calculate VC at 3 milliseconds and also our current at 3 milliseconds. So I'm going to erase some of this up here. So at 3 milliseconds, we're really just looking for the area A1 from before plus this new area A2. That should be easy enough for us to do. So 1 over 5 times 10 to the minus 6 amp seconds per volt. Our area A1 is the same, so 1/2 2 times 10 to the minus 3 seconds times 15 times 10 to the minus 3 amps. And then area A2 is a rectangle, so our base is 1 millisecond. And our height is 15 milliamps still. So 15 plus 15 is 30, divided by 5 is 6. If my mental math is correct, please tell me if I'm wrong. IC at 3 milliseconds is what?
$15.
15 milliamps. And from this, our power at 3 milliseconds is 6 volts times 15 milliamps, looks like 90 milliwatts. Easy enough. Lastly, we're asked to determine our energy stored by the capacitor at t is equal to 1 millisecond. Just as a reminder, the energy stored by a capacitor is 1/2 C V squared. So that means that we need V at 1 millisecond. So at 1 millisecond, we're looking for this area. Since it's a right triangle, it's just 1/2 base times height. So we're going to have 1 over 1 microfarad again. Our base was 1 millisecond. What's our height here?
Five milliamps. Oh no.
Is it 5.5?
It is neither 5 nor is it 5.5.
It should be 7.5.
7.5.
Yeah.
Yeah. So it looks like 7.5, and if it didn't quite look like 7.5 to you, we could easily find the slope. So 15 milliamps per 2 milliseconds is 7.5 amps per second. Multiply that by our time duration of 1 millisecond, and that gives us 7.5 milliamps. So let's see, 1/2 times 7.5 is going to be 3.75 over 5, looks like 0.75 volts. If I did that correctly, I believe I did. Just to double check here. So the amps cancels the amps. The 10 to the third times the milli cancels the 10 to the minus 6 down here. Seconds cancels seconds here. So let's see. Yeah, so 3.75 over 5, 0.75 seems legit. Plugging that in, we have 1/2, 5 times 10 to the minus 6 amp seconds per volt, 0.75 volts squared. Gives me 1.406 times 10 to the minus 6, or microjoules. And I'll be damned, that's right. So hopefully you guys feel that applying these relationships is about as easy as applying the inductor relationships was in Friday's class, because again, they're effectively the exact same relationships. Nothing too curveball related with regards to any of this, just direct application of the relationships, like what you'll see on some of your exam problems. I need to upload the practice tests so that you guys will see. I'm literally asking questions just like these. I had mentioned that there's a couple of homework problems that I really like. So let's take a moment to look at some of those really quickly. So the ones that I'm particularly interested in are homework 12, problem 3, and homework 12, problem 5. Let me pull them up on WebWork real quick. All right, so we'll look at problem 3 first. So in problem 3, we are given the following circuit, okay? And this may be one of the first times that we have specifically had to analyze a circuit containing capacitors and or inductors, and this particular circuit actually has both. So we have a time varying voltage source, Vs of t. We have an inductance here. I'm just going to say that it has a value of L. And then we have a capacitance here, and I'm going to say that it has a value of C. We are given a mathematical function for Vc of t. That'll be different for all of you. So that's why I'm putting things in this general form. And the capacitor voltage Vc of t is defined with a positive polarity on top. And our ultimate goal is to find Vs of t. So I want us to kind of talk our way through things here, okay? So does anybody have any thoughts on how we might approach a problem like this?
I would say define our equations for what we know. Like use our relationships to define what we know.
So we are definitely going to do that. So let me talk to you guys about my thought process here really quickly, and then we'll wind up doing what Austin suggested in a moment. Okay. So when I see this circuit, the first thing that I see isn't that, oh no, it's got an inductor and a capacitor in it. I see that it's a circuit with 3 elements connected in series. So whenever I see a circuit where all of the elements are connected in series, that screams to me, apply Kirchhoff's voltage law. In order for us to apply Kirchhoff's voltage law, we have to have voltage drops across all of our elements. So what I'm going to do is I'm just going to add in a voltage drop, VL of t, like so. So when I apply KVL around our loop, what I'm going to get is that the voltage that's provided by our source, Vs of t, which is what we're looking for, is simply the sum of the voltage drop across my inductor plus the voltage drop across my capacitor. Okay. So the voltage drop across our capacitor is a known quantity, right? So we don't have to do any work whatsoever to get that part. It was given to us in the problem statement. So that begs the question then, well, how do we find the voltage drop across our inductor? Any thoughts on that?
So the current will be the same?
100% correct. So our current, so let's draw that out here. I'm going to use purple. So our current I of t is going to be the same through the inductor and the capacitor, as well as the voltage source, if that mattered, but in this case it won't. So how would I go about finding that current I of t?
Since we're given the function VC, we just do 1 over VC to get VL.
So 1 over VC won't be VL because if we think about the units, 1 over VC is going to give us units of per volt. How is that equal to a voltage? Well, it's not. So let's think about the relationships that we learned today, right? So I believe that the current flowing through a capacitor is equal to C times the derivative of the voltage drop across the capacitor. That was the first equation that we learned for capacitors today, if I'm not mistaken. Does this look familiar?
Yes, sir. Dr. Hartman, I do have a question real quick.
Yes.
So just to clarify and confirm my assumption here, capacitance and inductance are not direct inverses of each other.
Right. So it's not like resistance and conductance. They are not
As
just
the-
simple
because
direct
it's different.
inverses of each other. No, they represent two different things. So they are electrical duals, but not electrical inverses. So just to clarify / reiterate, a inductor is an energy storage element that utilizes a magnetic field or current to store its energy. And a capacitor is an energy storage element that utilizes an electric field or voltage to store its energy. So their relationships are incredibly similar in that we can simply replace each other with I. Everywhere we have I, replace it with V. Everywhere we have V, replace it with I. But L and C are not just reciprocals. All right. So now that we have I of t, how do we find VL? So go back to your relationships that we learned on Friday, or it was one of the four, literally the first things I wrote down today during the inductor review.
VL equals L times the derivative of the current.
Exactly right. So we're just going to have L times di by dt. And so if I were to substitute in I of t is equal to C dV by dt, that's just going to look like LC times the second derivative of the capacitor voltage with respect to time. So just to be clear, that's me substituting this whole relationship in for I of t. So from this, our source voltage Vs of t is simply going to be whatever Vc of t is given in the problem statement plus Lc times the second derivative of that exact same capacitor voltage. And so obviously the answers will be different depending on, which function you get and all of that kind of good stuff, but this is how to solve that problem. Okay. So just to reiterate here, we had a circuit where everything was connected in series. So to me, and hopefully to you soon, if not now, that tells you apply Kirchhoff's voltage law. In applying Kirchhoff's voltage law, we had to utilize the relationships between current and voltage in our capacitor and inductor to sort out all of our unknown things. So before we move on to homework 12, problem 5, any questions about this particular approach? All right. So problem 5 is similar, but I think it's a bit harder. Okay. So here's homework number 12, problem 5. In it, we have a voltage source, and it is a time varying source once again. And then we have technically it's two capacitors in series. We haven't really talked about that just yet, but I'm going to call this CEQ. That's the next thing that we're going to talk about. And then over here in parallel with that, we have some inductance L. Here is our source current, IS of t. And now let's talk about what's given to us. Okay. So our source voltage Vs of t is a known quantity. Our source current Is at t is equal to 0 is a known quantity. And our ultimate goal is to find Is of t for t greater than 0. So any thoughts on how we might approach this?
Is it possible to convert one of these into another, or is that not possible?
What do you mean convert one of these into another?
Like, is it possible to convert our inductance into I'm sorry, into a capacitor?
It is not,
Okay.
or at least not with our current level of circuits knowledge. And this circuit is not sinusoidally excited, so we can't really do that anyway. But you wouldn't know that yet because we haven't covered sinusoidal analysis. We're not there yet. So we can't simplify the circuit in any way, shape, or form. We can't apply any type of transformation or anything like that. So, like I said, this is fairly similar to our last problem. But now, instead of having all of our elements connected in series, all of our elements are connected in parallel. So when I have a circuit where all of the elements are connected in parallel, what do you guys think I should do?
KCL.
Exactly right, Kirchhoff's current law. So what I'm going to do is I'm going to define a capacitor current here and an inductor current here. And so Kirchhoff's current law tells me that my source current, Is of t, is simply going to be the sum of my capacitor current, Ic of t, and my inductor current, Il of t. Okay. So let's work on our capacitor current first. So what's my equation for capacitor current? This should be equation number 1 from today.
Is it the derivative of voltage times the known capacitor value?
Exactly right. So we'll just have CEQ. So what's the voltage drop across our equivalent capacitance?
It's just the same as the source voltage, correct?
Exactly right. So we're just going to have CEQ times the derivative of our source voltage with respect to time. So there's our capacitor current. That's the easy part of the problem. Next, we need to figure out what our inductor current is going to be. So since the voltage drop across our inductor is Vs of t as well, we're looking for the equation that tells us how to find current when we know what the voltage is, which I believe should be equation 2 from our inductor lecture. So that would be 1 over L times the integral from, I'm going to say 0 here because we know is at 0 to t of vs at t prime, excuse me, dt prime plus il at 0. So we know what L is, we know what Vs is. How do you guys think we might find IL at 0?
We can just plug 0 in for the time value in the equation we just did.
Exactly right. So if we did KCL at our top node at t is equal to 0, what we'd find is that is of 0 is equal to IC at 0 plus IL at 0. And we could rearrange this to say that IL at 0 is simply IS at 0, which is a known quantity, minus IC at 0. Well, luckily for us, IC at 0 is pretty straightforward. That's just going to be, so IS at 0 minus CEQ times the derivative of VS with respect to time evaluated at t is equal to 0. So now we have all of the different parts, right? So from here, we could say that IS of t is CEQ times the derivative of our source voltage plus 1 over L times the integral of our source voltage plus IS at 0, which is going to be a DC term, minus CEQ times the derivative of VS evaluated at t is equal to 0, which will also happen to be a DC term. So this one required a little bit more thought. To me, the hardest part is figuring out how to get IL at 0. Everything else is, once again, just applying a simple circuit analysis technique, KCL in this case, and then using the relationships between voltage and current like we did in the prior problem. Okay. So realistically, in my opinion, homework 12, problem 5 is one of, if not the hardest homework problem that you guys were assigned. So hopefully this explanation gives you guys a big leg up on how to approach it. All right, before we talk about capacitor combination, are there any questions about this problem? Okay, so our last little thing to talk about is capacitor combination. So I'm going to ask you guys maybe an odd question, and if I need to do some math or analysis, we will. But how do you think capacitors are going to combine based on everything else we've done today?
It'd be very similar to voltage sources.
Not so. Voltage sources is kind of an odd thing to say because voltage sources in series combine easily, but voltage sources in parallel, not so much. How do you think it's going to compare to how resistors combine? I guess that would be a better question.
It's going to be the same, right?
It won't be. It'll be
Just the opposite.
It'll be exactly opposite of how we would expect. 2, I don't know, Jake Smith, did you intend to request an summary with AI companion? No, okay. Never seen that warning before. All right, so let's look at capacitors in series just really quickly. So let's say that I have a network containing some number of capacitors connected in series. So let's call this guy C1. Over here, we'll have C2 all the way out to some capacitance C sub n, like so. This is the voltage drop across my network of capacitances. This is the current flowing into my network of capacitances. And I'm going to define a voltage drop V1 across capacitor 1, V2 across capacitor 2, and Vn across capacitor n, like so. So if I were to apply Kirchhoff's voltage law around this loop, I would find that V of t would be equal to V1 plus V2 all the way out to V sub n. Since all of these capacitors are in series, they all have the same current flowing through them, which means I can express all of these voltages in terms of that common current, right? So that would look like 1 over C1 times the integral from negative infinity to t of I of t prime dt prime plus 1 over C2 times the integral from negative infinity to t of I of t prime dt prime all the way out to 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime. So there's a common factor of the integral from negative infinity, all that kind of good stuff. So we would have 1 over C1 plus 1 over C2 all the way out to 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime, or CEQ, excuse me, 1 over CEQ times the integral from negative infinity to t of I of t prime dt prime. So from this, we could say that CEQ is 1 over C1 plus 1 over C2 all the way out to 1 over C sub n, and then we have to take the reciprocal of the whole thing. So what does this look like as compared to resistors?
It's just C1 plus C2 plus C sub n.
So I guess what I mean by that is, does this look like resistors in series or resistors in parallel?
Parallel.
Parallel. So capacitors in series combine like resistors in parallel. So how do you think capacitors in parallel combine?
Like resistors in series.
Exactly right. So everything, even how they combine, is opposite of how inductors behave. Okay? So let me just write that down really quickly. Capacitors in parallel combine like resistors in series. So now that we have that sorted out, let's look at ICA problem 3. So we're given this big network here, and we're asked to determine the equivalent capacitance seen between the terminals when, for part A, the switch is open, and part B, the switch is closed. So this is a simple combination style problem, okay? So I'm going to identify and label my nodes. So let's call this node right here A. This will be B. This will be C. This will be D. This one will be E. And lastly, this one will be F. Okay. So in part A, we're finding the equivalent capacitance seen between A and D. So I'm just placing those on opposite sides of my screen. So let's start with the outside path first, because that's probably one of the easier things to sort out, right? So it's pretty obvious that to go from A to D around the outside path, I would go from A to B to C and then to D. So nothing real hard there. So here's B, here's C. So from A to B is 11. From B to C is 5 microfarads. From C to D is 18 microfarads. And we have taken care of this outside path here. So now we have our interior paths, okay? So it looks like I could go from A to E to D, or from A to F to D. So effectively, those two paths are going to be in parallel. So let's put E here and F here. To go from A to E to D, I'll go through this 18 and then this 15. And to go from A to F to D, I'll go through this 4 and then this 25. So before we begin doing any math with this, does anybody have a problem or any questions about how I redrew my network? Okay, so let's just start from the bottom and work our way up. So how do I combine 4 microfarads in series with 25 microfarads?
4 times 25 divided by 4 plus 25.
Exactly right. So 4 times 25 over 4 plus 25 looks like 100 over 29. So let's just put a single capacitor there. That's 100/29 microfarads. So what about 18 in series with 15? Should be the same thing, right? So that's going to be 18 times 15/18 plus 15, 90/11. So these numbers are going to come out gross, but it's okay. Somebody tell me what 11 in series with 5 in series with 18 is going to be.
$34 microfarads.
How did you get that? Seems like you just added the three of them together. Because I believe 11 and 18 is 29 plus 5 is 34. So you got to remember that capacitors in series combine like resistors in parallel. So when I did it, I did 1/11 plus 1/5 plus 1/18. And then I took the reciprocal of that and I wound up getting 990/343. Now I just have those three capacitances in parallel. And so to find the capacitance between A and D, I'm just going to add those together. So 990/343 plus 90/11 plus 100/29 gives me 14.51639 and some change microfarads, which seems to agree with our results. So whenever we're combining capacitors, we have to remember that they combine opposite the way that we would expect for resistors and inductors. Okay. All right, so let's look at part B really quickly. So in part B, our switch is closed. And so I'm going to erase this purple bit right here. And I'm simply going to continue node E like this. So really all that did is connect nodes E and node F from our previous example together. So our outside path is going to be the exact same thing. So I'm going to leave that as 990/343 because we've already done that part. Now let's look at our interior paths, right? So we're going to go from A to E to D, but there are two different ways to go from A to E, and there are two different ways to go from E to D. So let's put E here in the center. So my two different ways to go from A to E are through the 18 and through the 4. And my two different ways to go from E to, excuse me, this should be D, are so the 15 and the 25. All right, so what does 18 in parallel with 4 look like?
22.
Yep, just simply add them together. And what does 15 in parallel with 25 look like?
Forty.
Yep. Haley's doing all the heavy lifting today, apparently. So somebody else tell me how I would combine 22 in series with 40.
22 times 40 over 22 plus 40.
Thank you, Baylor. Exactly right. So 22 times 40 over 22 plus 40. Which gives me 440 over 31. And then now I would just add these two together. So for part B, we'd have 990 over 343 plus 440 over 31, which I got to be 17.07984.5 and some change. So 17.080 seems legit. All right, so that's all I really wanted to talk about for today. I think what we're going to be talking about on Wednesday and Friday of this week is much more interesting for what it's worth. Hopefully you guys agree. Anybody have any questions before we sign off of the Zoom for the day? All right, well, I hope you guys have a great rest of your afternoon, and I will see you on Wednesday, where we will begin discussing transient analysis of first order circuits.